need. And by the way, I'm here also the next week and probably 1,000 weeks after that, since I live here. So what I want to do now to wrap up the discussion of the theoretical description of the two-body problem is to map, is to wrap up this explanation about how we expand the green functions into this near and far zone. And that will take probably half an hour. And then in the remaining 40 minutes, I will speed through phenomenological applications. I mean, what are the things you have to know before you read the LIGO paper or things. So how the gravitational wave interacts with the detector, the geometry that give the geometry between the source, the detector, and the gravitational wave propagation that makes it, that it's important to analyze the data. And then yes, I will probably not do everything in 1 hour. So I will probably use, let's see where I get in this list. I will probably use some of the discussion section. But okay, let's start with this here. You remember, we had the potential, okay, the effective action, no? It was related to this integral. E omega t1 minus t2 e to the I k x1 of t1 minus x2 dt2, and then here there was the green function, which I take with the Feynman prescription, but in the near zone it doesn't really matter. And then of course there was this m1, m2, and the integral over dt1, the integral over dt2. This comes from the action of particle 1, this is the action of particle 2. Particle 1 is coupled to H00, particle 2 is coupled to H00, and then we contract H00, H00, and I get a green function. And then I told you, look, this is equivalent to do this kind of integral. Let me use the notation. When I put a omega or a k here below, it means that if they are Fourier variable, it's the omega divided by 2 pi, the k divided by 2 pi. If they are direct space variable, then it's just integral in that variable. So, and then I say, look at this. This will be, yes, integral over k of k squared 1 plus omega squared divided by k squared plus, I put the minus here, ak x12. Okay, and then I say, after all, when these guys are exchanging potential modes, these longitudinal modes, I mean, they are not on shell. They have a modulus of k, which is much larger than the frequency, than omega. And this you can think because you see the variation in the, I mean, think of the air going around the sun. The variation of the momentum on an orbit is sizable. Of course, the momentum varies of the order of the inverse of the size of the orbit, whereas the energy, does the Earth change its energy while it goes through the orbit of the sun? No, not really, no. So it makes sense to think that, you know, omega exchange between the two particles is much less than k. But mathematically, this cannot hold, no? This equality cannot hold, no? Because I integrate from omega from minus infinity to infinity, I integrate over all k's. So, but if I don't think about it, if I keep doing things like if this formula was correct, then I run into problem. And actually, it's good that I run into problem because when I use an approximation, at some point I should see the limit of this approximation. And the limit of this approximation is the following. I have an exercise about that, which doesn't appear now. Let's see if I can remember it. Okay. What is that? Okay, it's even better than I don't find it now. So, I mean, I will just convey what is really meaningful in this exercise. So, let's look at this diagram. So, we use this approximation where the time component of the change momentum is negligible. And then, so I have some momentum k, some momentum q minus k in some momentum q, okay? So I would expect here, this diagram would be something like, so there will be a ki, kj, I mean, that will related to the vertex here. So let's consider its leading order in V for the moment. And then I have some q minus k here, square, and I have a q square, and I have a k square. But then I will have to consider the expansion of small omega. I have to consider this for each of the propagator. So I will have something like 1 plus kv divided by k square plus ka divided by k square plus k fourth plus ka dot divided by k6 and so on. Okay, this is all this, I mean, this is very heuristic, no? Because when you remember when I trade this omega, when this omega gets in the numerator, then I integrate it here, and then I say, oh, an omega square is like dt1, dt2, no? And then a dt1, dt2, I hit here, this will give kv1, kv2. It's this piece. I call it VV, I mean, it doesn't matter here. Then when it's omega to the fourth, that will be d2, t1, d2, t2. And then this will create a lot of pieces. It will create a kv1 square, kv2 square, but this is not what I wrote here. Here I wrote a ka when, you know, the second derivative, the first derivative brings down a kv. The second derivative can act not on the exponential but on v and bring down and just turn a v into an a. And then the second derivative is this. Why I'm keeping only these terms? Because the other terms have higher power of k's in the numerator, no? Here, at the same order, I could have a kv square. This is clearly the same order, no? Because a is v squared over r, and k is k. R is the same thing as k. 1 over r is the same thing as k. So ka scales as k squared v squared, which is the same thing. But for the point of view of how problematic it is that clearly this is more problematic than this when k goes to 0. Okay? When k goes to 0, this is the leading term at this order. So this is v squared with respect to this, which is already one loop. This is v4 with respect to this, which is another loop. And this is v6. So you see, as I keep going on in this series, basically at the numerator, I always get a term with only 2 powers of k's. But at the denominator, I get k to the 4, k to the 6, k to the 8, and so on. So clearly, this expansion at some point will blow up in my face in the infrared. Okay, you see, because in the UV it doesn't mean anything, no? Because I have more powers of k up and down. So that doesn't do anything. But in the infrared, these are the offending terms. The numerator, I always have one term with only 2 and just 2 powers of k, whereas the power in the denominator grow and grow and grow and grow. So eventually, this will blow up in the Fourier space, in the infrared. Okay? And if you do the power counting, you see that this is the first order where it blows up. It's the 3pn relative order with respect to this diagram, which is already 1pn. It will blow up. And then you can see, okay, fine. Finally, I'm going to pay the price for this brutal approximation. This is a brutal approximation that is not supposed to be valid when k in the region of integration when k goes to 0, because when k goes to 0, eventually it won't be larger than omega, so this Taylor expansion won't be good. So, and indeed, this happens to blow up there. And then you can check the powers of k, because here I will have an integration over q, and then the Fourier transform over k. Okay? And so if you count, let's see, 6, 12, and here I have 2, 4. Okay, now the counting doesn't turn out quite right. 1, 2, so there is only 2 powers of k here. 3, 6, 8, 10. Okay, now I'm missing. Maybe I better find it in the exercises, but I can't find it. Let me check. Okay, but believe me, this happens. How come? This is not quite right. This is not quite right. Ah, yes, okay, I found it, yes. So I have 3, 6, yes. I have D3P, Ki, Kj. Then I have 3, and then I have, sorry. This was not P to the 6, sorry. This must be, so in my notes is K to the 4. How come? D3K, 1. Okay, this one. Wait, this is correct. Ki. Okay, so in my notes this is K to the 4, but it shouldn't be. How come? Okay, now I have 1 over P to the 4. PV. Okay, I have a mismatch here. I don't understand why. But anyway, so this diagram at reading order is 1pn. This should be 1pn of that. This is 1pn of that, which is 2pn, and this is 3pn. What am I doing wrong? Ka. No, I should be correct. Okay, anyway, let's not waste more time here now. I will correct this in the discussion section. 1, 2, 3 diagram. No, I mean, there's not much room, no? Because I have one integration, which is the Fourier space, 1, 2, 3 propagator, one element here, and then I have to expand. If I expand the first order, it gives me this. 2. 6. Okay, sorry. Yes, no, this is more subtle. Yes, this is more subtle. Actually, this piece is already divergent, but it's actually basically the coefficient of the divergence happen to be 0. But okay, I mean, yes, this piece is already divergent at 3pn. Yes, there is a divergence at 3pn, but it happens that, I mean, if you do the computation, the coefficient is 0. But okay, this is technical decay. So what happens is that the real physical divergence that you get is a 3pn relative order with respect to the leading order 1. But anyway, at some point this should happen, okay? Because you are increasing at will the power of k in the denominator, and then the powers at the denominator, you always have a pieces with only 2 k's. So you also have pieces with 6 k's, but you also have a pieces with 2 k's. So at the end, sooner or later, you must hit the infrared divergence. So an infrared divergence is very bad. So UV divergence, you can say, okay, fine. I'm using a modeling of 2 systems as point particle. Then to get a UV divergence, it shouldn't be too strange. No, it just means that my theory starts to be sensitive at the internal structure of the particle, which I set it to 0. So clearly, I mean, but an infrared divergence is very bad. But in this case, we know it's a problem of the approximation. It's not a problem of GR. So what comes out is that the solution to this problem is particularly subtle. So here I get eventually infrared singularity. Okay? So how can we fix it? Well, you see, we have done this. The solution of this is coming from the far zone. The far zone, you're going to think, okay, but in the far zone, I have only, you may say, well, but in the far zone, I have, I have my binary system, which from the far away I see as a blob, and then they couple to some long wave gravitational mode. In the far zone, I have all emission. Well, not quite. In the far zone, you can have emission, and then emission can be reabsorbed, or emission can self-interact and reabsorb, or can self-interact more than once. I mean, gravity is self-interacting. So all of this can happen. So you can look at Far-zone diagram in which there's no radiation to infinity. So basically, the way we represent it is that we collapse the binary system to one thick line. Here, of course, these two lines are interacting in a lot of ways, and that was the matching we sketched yesterday. No? So there is interaction. And then this can emit and reabsorb. And this can happen with the self-interaction. And how do I read it? Do I have a Lagrangian for that? Yes. It's the Lagrangian I wrote yesterday. So it's my integral of T00 coupling to H00 with 1/2. The dipole, I forget it. Then there is the 1/2 Lij coupling to H0i, comma j. This is angular momentum coupling to the gradient of H0i. And then I have my 1/4 Q quadrupole double dot coupling, let's say, to Hij. Okay? Questions? So all of this is already there. And there's no reason why this object shouldn't self-interact and contribute. So the highly, highly non-trivial thing is that if you sum this theory at short scale and this theory in large scale, basically here you will get a 1/epsilon ER plus some logarithm. And here you get some 1/epsilon UV plus some logarithm. And what can be here, the logarithm can only be, when you do the integration, you have, the only scale you have is R, and mu is the renormalization group scale, no, the arbitrary scale that you have to introduce in dimensional regularization. Here, the only scale you have is the omega of the gravitational wave, because the system has collapsed to 0 size. You cannot have anything else. And again, the two things sum up, and basically the coefficient of this singularity matches the coefficient of this singularity, and the two cancel. Whereas the logarithms combine. So you know the coefficient of the logarithm is always attached to the coefficient of the divergence. And actually here, to save dimension, well, if mu is a mass scale, so that R mu is dimensionless, then here should be omega divided by mu, of course, no? I have to decide. Mu is either a mass scale or a length scale. If it's an inverse length scale, then it has the same dimension of omega, so it has to go this way. So, and when you sum the two results, you see this coefficient must be the same of this, which is the opposite of this, because the two will have to cancel. And so at the end of the day, you get a logarithmic effect that goes as R omega. Okay, so you have a perfect cancellation of the mu scale, and you have a, yes, again, yes, this should be, yes. Let's say that mu is a frequency. This has to appear this way, no? Because of course you must have the same dimension of the same dependence on mu, but here the coefficient is minus this one, and so you get this. So the arbitrary scale cancel between the two, and then you get a logarithm with some coefficient that is fixed by the divergence, and this is physical. The coefficient is physical, and indeed this really gives a logarithmic contribution to the energy of the system. So all I'm telling you now is a story. Okay, this is just a story. I mean, you might say, oh, okay, but who guarantees me this happens? I will give you not a demonstration, but an argument that this is not too crazy to happen. So again, if you look from the far-away theory, you get a UV divergence. And the UV divergence is kind of natural, in the sense because look at this. I mean, you have collapsed the composite system to a point. There's nothing that guarantees that your results shouldn't be sensitive to the physics of what you call the point, but it's actually a composite system. So you get a divergence, and then you get something that depends on your only dynamical scale. For instance, here you have a quadrupole as in Fourier space. Quadrupole is a time dependent, in Fourier space is an omega dependent, so you get that. In this other theory, you get an infrared divergence, as I sketched earlier. And so you get a logarithm. So provided that your renormalization group scale is the same, that you're using the same regulator on both sides, the two things combine and give a finite result and finite and physical result. And you get this logarithm. So in all papers, in the old approach to the post-Newtonian, the people realized this problem. Actually, they realized also the near side of the problem, not the far side of the problem. And then you find written in papers that this shows a breakdown of the post-Newtonian approximation. I mean, it's written in the papers, but it's not really true. It's not a breakdown of post-Newtonian approximation. It's the breakdown of the near zone physics to describe all of the conservative physics. It means you that this expansion of the propagator, which is by definition the near zone approximation, cannot describe all of the physics at sufficiently high order. I mean, it's a breakdown of this expansion, not of the velocity expansion. And indeed, it can be fixed simply by adding the far zone coupling and far zone self-interaction. In particular, since I told you that the problem arose from this diagram, then you may think, well, there must be a diagram in the far zone that involves one triple vertex and which must match this other one. And by the power counting, you can already guess. So this will be a diagram with a 1G, 2G power, because 1G from here and 1G, because it's G order with respect to Newton, so it will be G square. And since it was 4pn, there will be a V6. So here you can think of this, the diagram that will give you the analog effect will be a diagram with the G power, a diagram with two quadruples, and with a mass. So if I say that this is a contribution to the energy, so this is, we scale as M1, M2 square. Yes. So this will be order of V to the 4. G m squared divided by square is V to the 4. And then there is a V6 that came from the third order expansion of the propagator. And then there is another scale of the mass. So overall, this is V to the 10, which is V to the 8 with respect to the Newtonian physics, which is a 4pn. So if you want to recover a 4pn contribution to the energy here, so you just have to add as many derivatives as you need to make the things match the dimensions. So you say, so first you see that there is a correct scaling with masses. So here there are 3 vertices, here there are 3 vertices. Each vertex brings a mass, so each vertex brings a mass. 1 mass from the quadruple, 1 mass from the quadruple, and 1 mass from the total mass. And the number of derivatives that you need must be something or the order. So how many do I need? So this is, dimension is mass cube times length to the 4th, okay? So if I want to make, and then I need time to the 6, okay? Because time to the 6, I write it as an L2, and G square M2 divided by L2 matches this, and then L4 divided by T4. Okay. Yes. Then okay, I have another problem with counting now. Was it possible? No, this is V to the 6. Okay, sorry. I should have overviewed this before. Okay, apparently there is, I mean, probably this problem with the counting is related to the problem of the counting I had before. Sorry, I don't see what is going wrong now here. So this is m cube L4 T4. Okay, you see here that this is G square M square divided by L2 is what appears here. Then there is a V6, here there is a V4. Okay. Okay, sorry. I will check this for the discussion section. So what happens is that you should have that a diagram with these powers, so quadruple, quadruple, and the mass should match this diagram suitably expanded and absorb the divergence and combine the logarithm to give a logarithmic physical effect. So you see, you get the heating of the divergence and you get a new physical effect with the logarithm that wasn't present at previous order, just because the logarithm only comes out when you have the divergence. So this is annoying. How do I get this wrong? Wait. Omega 4 is 4 derivative, 1 derivative. Okay. So there was a 4, okay, let me try to fix this, and if I don't do it now, let's do it later. Sorry for that. So this coupling is given, no? The fundamental coupling is Q double dot times H. So here I get an omega square, here I get an omega square, and here I get nothing, no? Because M coupled to H0, 0. Then how many, I get 3 propagators, so I get overall omega for the coupling, then I get 1 omega to the 6 because I have 3 propagator, and then I have an omega square for this vertex that only has 2 derivatives, they always have 2 derivatives, and then it's a 2-loop computation, and so it's an omega to the 6. So overall, this should be omega to the 6, so yes, it should be 3 derivatives. So it's correct. So this is correct. So this is probably has to be like this, but if it is like this, it's a 3pn. Yes, this matches what I found naively before, that it was 1, 2, 3pn and not 4pn. Okay, I will check later what is going wrong in this kind of argument. So this seems to be 3pn, and this seems to be 3pn. How can it be? No, the argument I gave before, this was the oh my God, it's 2pn, 3pn, yes. Okay, sorry, this seems to be 3pn, this seems to be 3pn, but it's wrong. I know it's 4pn. How can it be? But apparently the scaling gives me that. No, HQ double dot, HQ double dot. Okay, sorry, I will solve it later. I'm missing a v square at some point. Where am I missing a v square? I don't know. Okay, I will solve it later. But anyway, modulo this thing. So I'm just telling you a story. Modulo there is a v square that I'm missing, and the story is that this diagram is bound to give you infrared divergences, because when I increase the power of the Taylor expansion, I get higher power in the denominator of k square. And this is actually matched by some Farzon contribution, in which the system collapsed to a point, interacts only through radiation mode and eventually through longitudinal mode and longitudinal mode. But this is just a nice story. So let me try to give you some substance behind this nice story. So the substance that I will try to give you is the following. So in the full theory, you see, what we should do is we should do something like this. So we should take, at the end, the Fourier transform for sort of point-like particles with the full propagator. This is what the integrand in the full theory. In the near theory, what we did was to take the Fourier transform for this simplified propagator, for this expanded propagator. In the far theory, on the other hand, what do? We take the full propagator for these modes that are emitted by the composite system, but you see what is this expansion. This expansion, you see I put a gradient of the external field and I add a moment of the source. you see? I'm doing this. I'm expanding the exponential. When I do the this multipolar expansion, I am expanding, saying that the variation of the field is on a longer scale than the variation of the source. So I consider the source concentrated at the point, and its moment couples to gradient of the external field. Coupling moments of the source to gradient of the external field is exactly the same as expanding this exponential. So you see here, the near zone, the simplification comes from the fact that I don't have omega in the denominator. Of course, it's much more difficult to integrate in omega in case something that has omega here. It's much easier to integrate something that has omega as monomials. And in the far zone, yeah, I have a similar thing, but instead of expanding the denominator of the Green function, I expand the exponential I need to take the Fourier transform of. Okay? So look at what happens by doing this. What I'm going to say now is that, and I will give you kind of semi-quantitative argument of this, is that my full theory, that is represented by the full Green function and exact exponential, is equal to the near integral plus the far integral. I'm going to give you a plausibility argument that this is not too crazy. Well, this is what I want to demonstrate, but let me write instead an identity. I say that this is equal to, okay, let me check so I don't write it wrong. This is equal to, yes. And then so this is what I want to demonstrate, but actually what is true okay? So now it's an identity. Now you shouldn't complain, no? Because here I split the integral over all modes. I split on the integral over short modes and the integral, sorry, over long modes, small case, plus an integral over short modes, large case. Clearly, the sum of these two integrals gives the integral over everything, okay? So clearly, this is equal to the integral over everything of I minus n minus f. And so I minus n minus f plus n plus f gives me back I, okay? So this is an identity. Of course, this is a bit of hand waving. I haven't specialized this, and I'm assuming that I have only one propagator, and then I want to make the argument this applies to all loops. But okay, just follow the idea. The idea is that this is an identity written like this, because here I have I minus n minus f plus n plus f, and the integration over all momenta. But I want to show that only the first line matters, and then the second does not. Okay? I want to show you this. I want to give you a plausibility argument that this is the case. How it comes? Well, for k small, which means large momenta, for large momenta, I can do the exponential expansion. For large momenta, I can say that this piece, so sorry, for large scale, n is equal to, so, okay? So for large scale, for small momenta, I take my n, and I say, well, for small k, large scale, I can expand the exponential. Okay? And in this case, this integral is equal to 0, just because now I have only monomials of k, and in dimensional regularization, integral in d3k of k to the alpha, this is 0. Then, if you swallow this argument, then you can swallow also the analog here. If I take the far integral, and I want to use it for large case, for small momenta, well, then the far in this region is equal to clearly, the far is equal to this only in this region, and the near is equal to this only in this region. Because this is the definition of near, and this is the definition of far, and this is the definition of all. But in the near region, K small is far region, n is equal to this, and it's 0. In the near region, f is equal to this, and is 0 too, because it's formally the same integral. And in dimensional regularization, and so what do I get? That I cancel this in the far region, I cancel this in the near region. Okay, there is a caveat, no? Dimensional regularization only is true, it tells me that the integral of k to the alpha is 0 only if I integrate over all of the space. But basically this tells me that in the soft region, the total integral is actually equal to the far, and in the hard region, in the small scale, the total integral is actually equal to the near. And so this is 0, this is 0, and so I have demonstrated that my total theory is equal to the integral of the propagator in the near approximation plus the integral of the propagator in the far approximation. Okay, this is really heuristic now, of course, because first, I haven't used multi-loops. I assume only one integral. But, this is just the heuristic idea of why it is conceivable that the total result is exactly equal to the result of the near plus the result of the far. So if you find, there are papers for a formal proof with that. They are linked. They are mentioned, they're referenced to in the notes. But it's clearly the formal proof is beyond the scope of this course. I just want to give you a plausibility argument that is not too crazy to think that the sum of the two actually holds. And basically, yes, in the far region, the near integral are 0, and there is only this. In the near region, the far integral are 0, and you can very well approximate. But the theory is given by the sum of the two, so this is good if you take the sum over the integral over all region of momenta of near plus far. Okay, so this is the rationale behind this idea, that you have to take the near approximation and integrate over all case, and then you sum the far approximation and you integrate over all case, and then this recover the full theory. So yesterday somebody asked me if I was going to talk about the method of region. I don't see that person here now. Ah, yes, you are. And this is basically all what I want to say about the method of region. Okay? Yes, question. Thank you. Louder. Yes, the question is if there is an overlap between the two regions. Well, if there is an overlap, then the argument is screwed, and then it becomes wrong. So that's why separation of scale is crucial. If you don't have separation of scale, this argument doesn't work. But as long as you have separation of scale, yes. So when the two regions start to overlap, then the theorem doesn't apply anymore. Okay. So modulo this V-square mismatch that I will have to fix during lunch. So this is basically the picture. So in the near zone approximation, that means expanding the propagator in this way, you are bound to have to hit into infrared singularities, and it's good that they happen, no? Because otherwise you could keep going on order by order and think that everything is fine. But luckily, the infrared singularity is there. It's telling you, look, you are really doing approximation. You cannot trust this result to any order. And then the far zone dynamics enters. And then there is this hand wave argument that tells you, look, if you sum near zone dynamics and far zone dynamics, you get the full theory. Basically, in practice, you expand the green function. In the other, you expand, okay, I cancel it now. You expand the exponential, no? Because you have one mass at one point, the other mass at the other point. If their distance is small with respect to the variation of the gravitational field, then you take moments of the tense energy momentum distribution coupled to gradients of the field. That's exactly what the far zone approximation does. Instead of the exponential, you have the Taylor expansion on the exponential, and this is under control when k, which is the gradient of the field, is smaller than smaller than x. No, I mean, when this object is small, so that when k is 1 over lambda, where lambda is large, so k is small, and x, I mean, when this object is small, so you have a compact source coupled to a long-range field. Far zone expand exponential, near zone expand the Green function. So, as long as separation of scale holds, you can be fine with that. So the UV divergences in the far theory are also welcome, because it tells you that you are hitting into the fact that your system is a composite system and not a point-like, and nobody has to convince about that. I mean, of course, we know that the composite system is not a point-like. So the resolution of the UV divergences in the far theory are in the infrared divergences of the near theory. If you get an infrared divergence in the far, then this would be a real problem, because you know there is nothing a longer distance to match to. So if you get an infrared divergence, then you are really screwed up. But this doesn't happen, luckily. So the far zone is supposed to be a large scale. They're not supposed another theory at even larger scale. So this theory cannot have any infrared divergence, and indeed we haven't met any, so we are happy. This can have infrared divergences just because we know it's not complete along distances, and it will be completed by that. But this can have UV divergences, okay? On the other hand, this can have UV divergences because, yes, we are looking at the interaction of these two particles, but again, these are point particles. What happens when modes are so short wavelength that they can see the fact that the particle is not a point? Then again, it's natural to see UV divergences, but then you should be careful. So the UV divergences that we hit up to 5 pn, they're non-physical, in the sense that they're pure gauge. After all of this is done in a gauge fixed formalism, okay? So you should be careful that what you get is not a gauge artifact. And so up to 5 pn, all the divergences, UV divergences in the near zone that we found are ascribable to gauge artifacts. So you can gauge away with the change of gauge, so they're not physical. But in principle, at higher order, you could see UV divergences, and then you say, okay, look, now you really have to tell me what the point is made of. I mean, how big is the point, what is the Schwarzschild radius, or if it's an introstar, and so on. Then, I mean, it's absolutely natural that at some point you will hit some UV divergences in the near theory, because nothing tells you that everything works at any order, like if this particle were point-like. At some point, you must hit the fact that they have a finite size, and the finite size must show up somehow in your computation. So UV divergences in the near zone are nothing problematic. They are telling you just that your system cannot be modeled as a point particle. But you have to be careful. At 3, 4, 5 pn, you do find some spurious divergences, depending on the gauge you work in, of course. And then you realize, oh, look, I go to another gauge, or I go to a physical observable, and the UV divergences doesn't show up anymore. So it means that up to 5 pn, there's no UV divergences physically. Then, of course, in some gauge, they can appear, but you have to check carefully that they do not correspond to physical divergences that point to some inadequacy of your theory at short scale. Okay. Questions so far? So I move on? Yes, no. Question. Is there a proof that the velocity expansion that you explain is convergent, or will it break down in some order? Not that I know, but the velocity expansion. Yeah, actually, okay. Yes, there is a proof, it's linked in the notes, that you can do this near far zone separation but I don't know if I think the proof is perturbative. No, there is a proof in general that near far zone separation you can do, but it's perturbative as far as I know. Yes, I don't know if you can. But after all, this is all about perturbation theory. You're not supposed to use this outside the region of perturbation theory. So what I was sketching here was the recasting of that proof into the language of the velocity expansion. Alessandro Codella, are you happy with this answer? Yeah, I take the silence as a yes. Okay. So now we want to move to what do we want to do? Yes. Yeah, the finite size, just a final comment about finite size. So we know that our point particle theory is good. It doesn't show there are any divergences up to 5pn, so it's perfectly consistent. The near zone can describe the system of point particles at least at 5pn. But then you say, well, look, what happens? This is an effective theory, so in principle I should write down, I mean, all operator that I can possibly write down should appear somehow. After I integrate out all the gravitational interaction, at the level of effective theory, I should see something new. Like, for instance, why not a piece like this appear? Why not a piece of like this appears? At an effective level, no? You mean okay? So this is my fundamental theory. But then at an effective level, after I integrate the gravitons and I obtain the potential, why this system, these objects are allowed by general covariance, they should appear. So actually, do they appear? The answer is yes, they do appear, and actually related to the UV divergences that I was mentioning. Again, this is only qualitative. So if you do this computation, you do hit into UV divergences, and you see that the counter terms can be eaten back if you add, with the suitable coefficients, World-line terms of this type. So World-time terms of this type are not in the fundamental theory. They are not something we started with, but since the two-body potential happens to have some divergences that can be eaten back if you add these terms, then you say it's like that if these terms are generated at an effective level. But this is standard in effective theory, no? So you start with the Lagrangian dictated for the fundamental, you do some effective interaction, and then you see, oh, everything looks like if I generated this term at an effective level. So it happens that these terms are zero in a good gauge, in a physical gauge. Why? Because particle 1 should only see the Riemann and the Ricci scalar of the other particle. But what is the Ricci of particle 2 at the position of particle 1? You remember the Einstein equation. It's local between Ricci and energy momentum tensor. So if the energy momentum tensor is 0, Ricci is 0. Okay? So the Ricci of particle 2 at the position of particle 1 is 0. The Ricci tensor of particle 2 at position of particle 1 is 0. Okay? So the fact that I encounter divergences and they're possible to absorb into counter terms of this type is yet another confirmation that those divergences are spurious and they just belong to gauge artifact. But then you say, oh, okay, but then I can do this. What about this? I get a Riemann square. No, that one is there because the Riemann is non-zero even well outside the source. Okay, so the Riemann of particle 2 is non-zero at particle 1, so this term should be generated. Okay, and how do we check what is the leading order contribution to the potential of this term? The leading order contribution of this term is the following. The leading order contribution of this term is the following. So it's a Riemann square. So if the linear part of it is 0, it's Riemann square. I need at least 2 h's. And then I get 1 h coupled to the h00 of the other guy, 1 h coupled to h00 of the other guy. So you remember, this diagram we already knew it was 1pn if it was given by the standard Lagrangian. So I get 1 over r from this, 1 over r from there. So this diagram is g squared. But here now I have the Riemann is 2 derivatives of h. So overall I have 4 derivatives, which is adding like 4 r's. So then, of course, there must be some mass scale here in the front to save dimension. So this is 1 over length to the 4th. 1 mass should have been there anyway. So there must be 4 additional masses to match. So this diagram must go like this. So the r to the 4 extra is given by the fact that each Riemann brings 2 derivatives. So with respect to this diagram, that the leading order was g squared over r squared, this diagram will be, so it would have been r squared if there wasn't this extra derivative here, will be r squared. So it will have 1 over gm over r. So it's 4 pn, sorry. This is already 1 pn. So this object will be 4 pn with respect to that. So overall will be 5 pn. So in principle, I can get at an effective level the generation of a term like that at 5 pn interactions. So what happens is that while this happens for neutron star, this doesn't happen for black hole. And the reason it happens for black hole is not completely well understood. There are some good explanations, but not completely well understood. But we know that the coefficient of this term at 5 pn is actually 0. Yes, question? Yes. Yes, because think of the Einstein equation, no? R min E is proportional, I mean, T min E. So the other particle is located away from particle 1, okay? So, I mean, your T min E here is 0, okay? So the R min E generated by your T min E here is 0 because of the Einstein equation. So this holds for the Ricci and for the Ricci tensor, Ricci scalar, Ricci tensor, but not for the Riemann, okay? Because the Riemann, we know the solution, no? The Riemann is non-zero all outside the space, okay? And the Riemann, we know now what is its scale. The Riemann is of the order of, if the Riemann source by mass m at a distance r is order of this, gm over r cube. Or if you like, it's 2 derivatives with respect to gm over r. That's what I wrote here, no? This diagram, this piece of the diagram gives you gm over r, this piece of the diagram gives you gm over r, but then if instead of having a00 square like in the fundamental Lagrangian, here I have a Riemann I must attach 2 more derivatives here, 2 more derivatives there, and 4 more power of the mass to compensate dimension. So this gives me overall r to the 4 with respect to the diagram in the fundamental theory. So overall will be a 4 pn correction to this 1 pn diagram. So overall it's a 5 pn correction. So 5 pn correction are the first order correction for a spherical object. So if you have a spherical object, the fact that it's actually spherical and not a point should give you a correction to 5 pn 5 pn new terms in the potential. So this happens for neutron star, and actually, you know, it's very important that these effects are there, because depending on the equation of state of neutron star, the mass of the neutron star is distributed in some way or in another, and this actually affects the coefficients of this. So actually, if you see this effect in the waveform, you can actually have a clue of what the equation of state of neutron star is through its mass distribution. But in GR, this coefficient is 0 for black holes. So this has been a puzzle. I mean, it's still sort of a puzzle. But there are people who seem to have a nice explanation. But okay, it's a fact that this coefficient is 0 for black holes. And indeed, so if you compute the effective potential for black holes in the near zone, up to 5 pn, you get no physical UV singularities. You can really treat the black holes as point particle for sure up to 5 pn, because you really don't need the inclusion of this there. For neutron star, no, for neutron star you have this term, and this term has a coefficient that depends on the equation of state, and actually it has even been measured. In the only event of the two binary neutron stars that has been accompanied with the electromagnetic counterpart. So it has been seen that if you use the point particle approximation for the waveform, it doesn't quite fit as well as if you fit the waveform with the inclusion of this effect. And actually, you can fit this number from the data, and that number, the best fit is away from 0. So to some extent, it has been measured for one case, and which is the case, basically, of two neutron star that will have some finite size effect imprint in the wave. OK. So this is all what I wanted to say for the formal part of gravitation, of the two-body modeling in gravitational wave physics. So now I want to move to the phenomenological part in the remaining 20 minutes. Yeah, but then it might be a good time to pause for questions. OK, so I cancel, and questions there? No, no more questions. So maybe I'll skip this, because then we'll soak up 10. Yeah, let me go straight to this, and then we'll see if I have more time. OK, so the idea is now, let me jump now to the detector. No? You remember that you must have seen many times what is the spectra, the square root of the spectral noise density. It has this shape from 20 Hz to 1 kilohertz. So what is the, and this is not a dimensionless number, but it's Hz to the minus 1/2. So what is the idea? The idea is that if you take the output of the detector, then it will be noise plus signal. But the signal will be very, very much smaller than the noise at any instant of time. But the signal will have a specific frequency evolution that is handled to disentangle from the noise. So the idea is that we want to take the output of the detector and filter it so that we enhance this and we kill that. So the idea is the following. So we want to filter the output of the detector by correlating with some filter K. And we say that, OK, our filter K is optimal. It actually matches the shape of the signal. And so it has 0 correlation with the noise. OK, this is not quite true for all the possible signal that you have. But let's assume, I mean, the noise, after all, the noise in the detector, I mean, there will be some physical noise in the sense that something happens to the mirror, something happens to the laser, and you see, I don't know, somebody bumping on the ground, induce a vibration. That is actually a physical effect. It's just not gravitational wave. It's not astrophysical, but it's physical. But let's forget about those. Let's assume that there are just random fluctuations in all possible device of the detector. And so this random fluctuation has 0 correlation with our filter. And then we want somehow to check, I mean, a figure of merit that you always have to consider when you do comparison with the experiment is signal-to-noise ratio. And so we want to check the ratio of the signal, I mean, to see how strong is the signal. I mean, it's impossible. I mean, that's a natural, common thing in physics. You don't say that something is strong or weak. You only say that something is strong or weak compared to something else. And so it makes sense here to say that something is strong or weak with respect to noise. Okay. So you cannot compare exactly straight to noise just because, I mean, if you try to do this and then you get that your signal to noise ratio that you are trying to build will be linearly dependent on your filter. So you put twice the filter or half the filter, you see, that will reflect in the signal-to-noise ratio. So you say, but it's okay. I also filter the noise with the same filter, so if I rescale the filter by any number, this ratio is independent of that. And then I will get here in this filtering, I get just the signal magnified, and here I get, oh wait, here I get 0. I cannot do this signal to, this is not a meaningful signal to noise ratio, no? Because I get signal filter and then I get noise filter, but this has to be 0 because I want my filter to kill this and pick only the signal. And so this is not a good proxy for the signal to noise ratio. So can you see what would be a good proxy for the signal to noise ratio? If I take 2 copies of the signal, the noise square, and then I average over many realizations, this is not supposed to be 0. Okay? And this will give me a proxy for the noise square. But then I take the square root here. So then here I get a possibly good definition of signal to noise ratio. I have the output of the detector correlating with the filter, and then I don't have really the noise, but the noise square correlated with the filter. And actually, this quantity, actually this is done in Fourier space, so let's do it in Fourier space. And here, this quantity is actually what we really want to monitor with an experiment. So suppose I have some noise, and I monitor it for 1 hour of data, and then I Fourier transform it. And then I have the same noise stretch, and I want to correlate noise at different frequencies. Okay, so the Fourier transform, it's a complex number. So this will have an amplitude and a phase, e to the I phase here, e to the I another phase there. So if the noise is really random, when I do this, I take 1 hour of data, take the Fourier transform. Then I take an hour of data, Fourier transform. Another hour of data, Fourier transform. An hour of data, Fourier transform. I assume that the amplitude of the noise will have some fluctuation, but will respond more or less in the same way. Whereas the phase at each frequency, when I take the Fourier transform, will oscillate wildly. Okay. So basically, what I will have that for each frequency, in one realization, the phase will be pointing here. In another realization, the phase will be pointing there, and so on. So basically, if I average over many realizations on this 1 hour stretch of data, I assume that I will obtain 0 correlation unless delta f and f prime are one minus the other. So I put a star here, and I say unless f and f prime are the same. Of course, if f and f prime are the same, the phases are phase and minus phase, so they never average to 0. But for all other frequencies, I assume that if I average these over many, many realizations, I obtain a delta of f minus f prime. And so this cannot be the end of the story, because you see the output of the detector, we take it dimensionless. So this is the Fourier transform, it has dimension of time. This has dimension of time. This has dimension of time. So this is dimension of time square, and this is dimension of time. So to save dimension, here must have a function that is called the spectral noise density. So the spectral noise density is the real fingerprint of the noise of the detector. And another thing which is important is that, I don't know if I keep saying this all the time, so I don't know if I said it in this course or not, is that if you take the Fourier transform of 1 hour of data, or if you take the Fourier transform of 2 hours of data, the amplitude of the Fourier transform changes, no? Because suppose your sampling is 1 second. If you take the Fourier transforming of 1 hour of data, you have 306,000 sampling. If you take 2 hours, you have twice as many, 7,200. The amplitude scales as the square root of the number of samples. So it's clear that this is not a good proxy of the amount of noise in your detector, because it depends on how long did you sample it for. So you say, oh, my detector has such and such noise if I sample for 1 hour. And people will laugh at you. Hey, come on. I want something intrinsic about your detector. And the something intrinsic of my detector is exactly this. Because this, if you go to discrete, no, will be a delta of what is the property of a delta in continuous space? It's something that you integrate over df, it gives you 1. And this is exactly the same thing in discrete space. It's, you multiply by the spacing of the frequency, and this is delta f prime, and this is SNF. So this is the object that scales 1 over delta f scales with the length of your chunk of data you use to take the average, and this is object is really intrinsic of the detector. So it makes sense to make the plot as a function of square root of Sn, because Sn is quadratic in the noise, so square root of the Sn is really linear in the noise, and is really an intrinsic property of the detector. It doesn't depend on how many chunks and how long the chunks you use to take the average, okay? So this is the thing. So now, when we go to Fourier space here, we can replace this object by spectral noise density filter modulo square, the delta allow us to kill one of the two integrals, and so we get this. Sigma of f times k of f. Okay? So now this is my candidate signal to noise ratio. So it has all the nice property that is linear in the signal. It goes as 1 over the noise. I mean, if the noise double, the signal to noise ratio becomes 1/2 of it. It's independent on the normalization of the filter. If I scale the filter by any fixed number, it stays the same. And so this is a good candidate of signal to noise ratio that fulfills all the properties. There is just one piece missing. What is k? How do I choose k? Then you might think, oh, okay, I must choose k as aligned as possible to the signal. So here I get signal noise square, here I get signal noise square. Oh, no, wait, it cannot be really aligned to the signal, because then it also appears in the denominator. So how do we solve this problem? Well, it turns out that this problem has a very elegant solution if I recast this into a scalar product. Then I say that I take two vectors of an L2 space, and I say that the scalar product between these two vectors is given by A times B star divided by Sn. This is my definition of scalar product. And is it true? And then, yes. And then I say that this object is look like my signal multiplied by, so scalar product with my filter Sn divided by filter Sn, filter Sn. Is it true? Let me check if this is true. So with this definition of scalar product, so to 1/2. With this definition of scalar product, the numerator is signal times Ksn divided by Sn. So yes, it matches this. In the denominator, this should be filter square multiplied by Sn square divided by Sn, because of the definition, and this. So if I call this U, this is SU, scalar product divided by norm of U. Okay? So, and U is my unknown. So what is the U that maximizes the signal to noise ratio? Yeah? U equal to S. So clear, this is a scalar product. I mean, I have to take a scalar product between S and, let's say that U is normalized. So I get rid of them. I have to take a normalized vector and project it into S and maximize this projection. Well, I take U equal to S, normalized. Okay? This is clearly the choice. And anyway, since this is independent on the normalization of the filter, I can get rid of this. I mean, I know the signal to noise ratio doesn't change. Okay? So if I take U equal to S, I'm fine. But U was equal to K times the spectral noise. Okay? So the optimal choice of the filter is signal divided by spectral noise. So if I substitute in there, the signal to noise ratio optimal is signal times signal divided by spectral noise divided by spectral noise, signal modulo square divided by spectral noise square. okay? And so at the end, the signal, so this is clearly the square root of this, so overall, this gives me signal modulo square divided by the spectral noise, 1/2, okay? So this is the mathematically optimal signal-to-noise ratio that I can have by filtering the data. So you see, the filter doesn't have to be optimal, exactly equal to the signal, but it has to be the signal where I kill the part with a lot of noise. No? Basically, if my signal, and we'll demonstrate in a second, has this shape, and it does have this shape, and this is the noise, my filter doesn't have to have the same shape, but has the same shape where I suppress, I mean, where the noise is flat, the filter is roughly the same shape of the signal. But when the noise is large, my filter kills the thing I want to correlate. So when I want to correlate the signal with the optimal filter, the filter has to pick the features of the signal that are above the noise. The features of the signal that are below the noise, I kill them, because otherwise I'm picking the noise, okay? Because otherwise when I take the correlation of the filter with the output of the detector, I'm not picking the signal, I'm picking the noise. So this is the idea of the match filtering. And by the way, this is what standard radio do. I mean, now radio are electronic, but you know, the old radio, you have a dial, and you turn the dial, and what does it do? It changes the frequency of reception by moving a small condenser, okay? So if you turn on the radio at a random frequency, you just hear noise. Shh. No, of course, because you're picking noise. But then you tune your dial, so you tune the filter to the signal, but only in that band, where the signal is above the noise, and then you hear. If you tune the filter to another band, you hear only noise. Okay? So here things are a bit more complicated because the radio signal are concentrated in a very, very narrow band, are modulated, but concentrated in a very narrow band. So if you're flat in that narrow band, it's enough. For us, it's not like this because this signal has a specific features. So, and you want the filter to carry all of those specific features and just kill the features that happen to be in the frequency where the spectral noise is large. You just kill the features where the spectral noise is large. Indeed, the noise, if you really look at the real noise, is not like this. So it has a lot of spikes, no? Because there are suspensions to the mirror. And the suspensions, no matter how well you make them, I mean, they will have some frequencies at which they go to resonance. So if a perturbation arrives exactly at the resonance of the suspension, then you get these huge spikes. But those, you see, in frequency space are very narrow. So what do we do in the filter? That it means that you take the signal and you just chop out in frequency space a very, very narrow region. So it doesn't bother too much, okay? So if the output of the detector has a huge noise component at some specific frequency, so it's basically a cosinus, and my signal is here, with a specific frequency pattern, you see this huge noise component, it doesn't really bother, because you see, it corresponds to having a spike here, whereas my signal is broad. So it means when I take the filter, I just chop out this part of the signal, and I'm happy with the rest. So you see, this huge noise component, provided it's not broad in frequency, of course, but if it's a pure cosinus, it doesn't bother me. And that's actually what happens, because this nice curve is just the design sensitivity, but the real curve has a lot of these ugly spikes. Indeed, you see in the LIGO band, in the LIGO detector, you see a huge spike at 60 Hertz. And in the Virgo detector, you see a huge spike at 50 Hertz. And you can guess, that's the power line. You see, in US, the power line is 60 Hertz. Somehow, it leaks into the noise of the detector. And in Virgo, it's at 50 Hertz, and it leaks into the power line detector, plus all the suspension. So now I don't have time to do the Terror F2, do I? Yeah. So basically, this shape that I sketched here is actually computed analytically. So if you take the waveform that we computed, which is Q double dot divided by the distance, and then you say that you plug in the actual, this is something like the kinetic energy of the system divided by the distance, and we know that the velocity is changing. You remember that we derived on Monday, no? We derived how v dot changes with v. If you fold in this information for how v dot changes with v, you see that the frequency of the inspiral part of the waveform goes as f to the minus 7.6. This can be done quite easily analytically, and it's one of the exercises. There is one thing that should be worry you, though, because every time I sketch the waveform, I write it as something that increases the frequency and increase the amplitude. So a higher frequency, it has higher amplitude. Then I take the Fourier transform, and I'm telling you that at higher frequency, I have lower amplitude. I mean, wait, which of the two pictures is wrong? Is it true that at higher frequency I have higher amplitude until there is a cutoff, and this cutoff is given clearly by the size of the system, which is the inverse of the mass? So you understand the apparent puzzle? You expect that the fact that the amplitude grows with frequency would show up in the Fourier transform, no? You expect that this frequency beam should be mostly sourced by the time stretch of the waveform which has that instantaneous frequency. So if you take the maximum frequency, that should be sourced mostly by the end of the waveform. The end of the waveform is higher amplitude, so how comes that the amplitude of the waveform goes down with frequency? Okay, my students should know the answer. So, but all the others, have you ever thought about it qualitatively, how this happens? So the exercise does the computation analytically, and you find this behavior analytic. But what is the physics behind this analytic behavior? Well, you remember, v dot over v was something like v to the 8. Let's redo it. So v dot over v is something like e dot over e. E dot is v to the 10. E is v to the, yes. V dot over v is something like v to the 8. So the rate of change of velocity, and which is proportional to the rate of change of frequency, where it is larger, here or there? I mean, is frequency changing fast? Here or there? Frequency is changing fast at high V, okay? A small v is changing very, very slowly. So it means that to move from one frequency to another deep in the spiral, it takes a long time. So there are many, many cycles that contribute to a frequency being in the small frequency. And there are few cycles that contribute to a frequency being in high frequency. So this instantaneous amplitude is larger, but there are only few cycles that contribute to it. Whereas, you know, when I go behind, there are many cycles to contribute to a low frequency being. And this is the reason why at low frequency the amplitude is larger, at high frequency the amplitude is lower in Fourier space, despite instantaneously, I have a high amplitude at high frequency, a small amplitude at small frequency. But you see, the small frequency, they pile up because many cycles, and they build this strong signal. Here, whoop, you've seen this in the LIGO thing with the whoop, the chirp. The LIGO presentation where the signal is translated into sound waves. Here is very fast. So the signal sits very, very little at each frequency beam. So it leaves very little power at each frequency beam. So this is the inspiral. Then numerical simulation tells us what happens in the measuring down. Basically, there is a kind of flattening until you get to the cutoff. So this minus 7.6 flattens. And actually, it can even go up a little bit. And the fact that it flattens or goes up, it's a strong measure of the spin. But this, I mean, I don't have time to explain you why. But this is just to tell you that this part is completely fixed by this analytic computation. This part, it's hard to tell with analytic computation you do with the numerics. And then people realize that it goes flattens or can even go up depending on the spin. And actually, there is simple qualitative reason for that. Is that if the two objects has a lot of spin, you know, the sum of the two spin can even exceed, would make a black hole with the sum of the angular momentum plus the two spin would exceed the Kerr limit. So what does it has to do the system? Since the final black hole cannot exceed the Kerr limit, things are arranged so that the two black holes repel each other and they sit a lot of time there until they radiated enough angular momentum so that they can finally merge and form a Kerr black hole that doesn't exceed the Kerr limit. So you see, when you have a lot of spin aligned, so the two things, instead of going smoothly into merger, they kind of repel each other because they say, oh wait, we are forming a black hole that exceeds the Kerr limit, so we better wait and radiate more angular momentum until we merge. And this is the reason why for high spin, you get a lot of cycles here at the end, so you have a lot of cycle contributing to this final frequency bin, and so you get a peak for high individual spin in this. But okay, this is a qualitative feature. So in general, here, the system flattens down, and unless you have these really finely tuned spins so that they arrange and they try to overcome the Kerr limit. Okay, so this I will leave as an exercise. So the interaction on the detector and the relationship with the angles, yes, I cannot do it now, and also the cosmological thing I will probably explain today into the exercise. Okay, so I left out a few things, so this probably will motivate you to study more. Thank you.
So perhaps it's better to postpone your questions to the discussion section, as we are running a bit late. And okay, folks, so it's lunchtime. We'll be back at 2 p.m., right?